Hello, today we're going to study the operational amplifier called the op-amp. So it's a standard five-terminal device where we have two input terminals. This is the non-inverting input terminal. This is the inverting input terminal. So we denote it by plus and minus sign. And these are two supply voltage. One is positive and one is negative, and this one is the output terminal. So the way we will go ahead in the lecture is we'll begin with the ideal op-amp and some of the assumptions we take. We will look at the open loop characteristics of an ideal op-amp, and we then look at the closed loop amplifiers and how they are derived from the first principles. And then afterwards, we look at some of the applications, some practical amplifier circuits, and some non-idealities. All right, moving on. Let us first understand what an op-amp actually does. So it has two input terminals. One is marked with the plus sign and the one with the minus sign. And the op-amp continuously compares the voltage at these two inputs. So if the voltage to the plus input is slightly higher than the minus, the output moves to one direction. And if the minus input is higher than the plus one, the output moves to the opposite direction. So the small difference between these two input voltage is called the differential input voltage. And op-amp multiplies this difference by a very large number, which we denote as the open loop gain. So we assume that it's almost infinity. And for an ideal op-amp, we make these three ideal assumptions, basically. The gain is infinite, the input resistance is infinite, and the output resistance is zero. And from these assumptions, we get two useful rules. One is the virtual short, basically stating that the input open loop gain is very high. Thus, the input voltages are almost equal, and no input current, so the input resistance is infinite. That means that there is no current flowing at both of the terminals, and they're equal as well. All right, moving on. So let us understand what happens when an op-amp is operating without a feedback. So let's look at this graph carefully. So the horizontal axis shows the difference between the two input voltage, and the vertical line shows the output voltage. At the center of the graph, basically the two input voltages are almost equal, right? And in this very small region, the output changes in proportion to the input difference. So, but this line is very steep, right? Because the op-amp has a very large open loop gain. So let's say we move slightly to the right, right? Let's say here. And this means that we will get an output voltage equals to this, 5 volts. But we just moved by like very small margin. And if we move towards the left, let's say by this, we'll get a negative 5 volt at the output. So very tiny difference in the input variation creates a very large output voltage swing, and this is very unstable for operation. We want a very controlled amplification for our circuits, right? So this property is not really useful for application, and in real life, we use the feedback loops to control the amplification, and we will discuss it in the coming slide. Let's go ahead. All right, let's close the loop down. So in this is called a non-inverting amplifier because the input voltage is at the non-inverting terminal. So signal is applied here. There is the feedback resistor and uh, dividing resistor, voltage dividing resistor. So suppose the output shoots very high, right? The feedback voltage will also rise, thus reducing the difference between the two inputs. So the op-amp then corrects the output voltage downward, right? Because that's how we have seen in the previous graph that the changes in the differential input causes an output voltage swing. So since there's no current, since this is applied here, so there's no current entering in this negative terminal. And this RF and R1 creates an unloaded voltage divider, such as V minus goes to V naught multiplied by R1 squared by R1 plus. I apologize for my poor handwriting. And we know that the V minus and V plus are equal, and they're equal to V in. So then we can replace it, and we can say that, okay, V naught by V in is equals to this ratio of the resistance. And if we divide like V naught by V in, we get the gain, right? So now we have come from a point to the next point where we're controlling the gain by a set of resistor ratio, not by the open loop gain. So now Using feedback, we are having a very good control over the gain of our amplifier. Now let's look at the inverting amplifier, right? The positive input is grounded and the negative input holds the input voltage. And this point is basically called a virtual ground. It has the reason we call it virtual ground because it's not physically connected to the ground, but it has approximately zero voltage. So when the input becomes positive, the current flows through R1 towards the summing node. And since no current can enter this input terminal, as I've mentioned, the input resistance is very high up and up. So all the currents will flow through the feedback resistors to the output terminal. And if we apply the Kirchhoff's current law, it gives us something like this: Vn divided by R1 plus V naught divided by Rf equals to 0. And therefore, we can have something like this: V naught equals to minus Rf by R1 into Vn, right? And if we divide V naught by Vn, we get our gain. And it becomes the ratio of the two resistors that are being used. And the minus sign comes because it means the output is inverting because we're applying the input voltage at the inverting terminal of the op amp. So the output is inverting. That's why it's called an inverting amplifier. So it means that if we have a input voltage like this, the output will look something like this with an inverted phase, right? That's why we use the negative sign here. All right, let's move on to the next slide. So now you look at a very special case of the non-inverting amplifier. This is called a voltage follower or the buffer circuit. Here, the output is connected directly to the inverting input, and to follow basically the input voltage. So the closed loop gain is 1 here in this case. And in other words, if the input is 2 volts, the output is also approximately 2 volts. And the follower does not increase the voltage. It is very useful because it draws no current from the source and it can provide more current to the next stage. Let's look at the graph on the right. This axis represents the input voltage and this one, the output voltage, right? And the central straight in the central straight line region, the slope represents the amplifier gain, and the voltage follower has a slope of 1. So while a gain of positive 3 will go up like this, and a negative 3 will go down like this, the voltage follower will have from like straight line basically. Because the output, so these lines will not affect the voltage follower circuit here. And when the output reaches these maximum saturation limits of, basically these are the voltage rail limits in the op amp, the graph becomes flat. So it means that no matter how much we increase the input voltage here, we cannot go beyond a certain limit of the op amp. So let's say this is 12 volt. Let's say our supply rails here, these pins, VCC is 12 volts, VEE is negative 12 volts. So if we put 15 volts as input, it will still stuck at 12 volt or negative 12 volt. So it cannot go beyond these pin values. All right, moving on. So let's look at two applications before we conclude. So one is a summing amplifier. So the virtual ground concept naturally relates to a summing amplifier because each input voltage is connected through its own resistors to the inverting node. And since that node remains close to 0 volts and each produces an independent current, so we have a Kirchhoff's current law, which gives us this. Basically, this is a summing point. These two currents, I1, I2, gets added up here. I3 equals to 1. And flows through these feedback resistors and comes here. And the circuit, these kind of circuits are basically used in audio mixers where we have several channels combined with binary weighted registers, and it can also perform a simple digital to analog conversion. So it's not really a new principle. It's simply an inverting amplifier with several inputs meeting at a same virtual node. All right, the difference amplifier. So sometimes the required signal is the difference between the two voltage rather than either voltage measured from the ground. So with properly matched resistor ratios, the difference amplifier produces uh, an output voltage like this. V naught is equals to R2 divided by R1, and the difference between the two independent input voltages. And this basically amplifies the difference, rejects what is common in the both input. So there's something called common mode rejection that is indicated for these kind of amplifiers. And a voltage appearing equally in both inputs is called a common mode signal. So basically, they will cancel out each other ideally. But if there is very tiny difference in the input voltages, they will get amplified and we'll be able to see it in the output end. So this is really useful for cases such as Wheatstone bridge, strain gauge, and pressure sensors. So yes, that's my presentation. Thank you. And we'll discuss more in the next lecture.